All right, so in this video, we're going to be looking at polynomial and rational inequalities. We're going to do one example of each, and we're going to talk about how similar or different they may be. And we may even look at how you can treat a rational inequality somewhat like a polynomial inequality, and then just deal with the zero behavior differences for factors that are coming from the denominator. But some of the strategies that we're going to look at are going to be similar in both cases. So we're going to start with the polynomial case. And then the main idea for both of these is we want to be able to compare these to zero, because that gives us the ability to factor. And we don't have that when we can't factor, when we don't have a zero. So what we're going to do is the same way we would do if we were solving the equation for equal to zero. We move everything to one side of the problem, and then we go from there. So I'm going to move the 9x squared over, greater than 0. And then we factor. Now, it's very tempting sometimes for wanting to just like cancel out the things that we can divide everything by something, but then we lose values, and so we can't do that. So instead of dividing out, for instance, the common x squared, we're going to factor it out. And that's going to give us two possible zeros. We're going to have a 0 at 0, and a 0 at 9. So let's draw our sign chart. Zero and 9. Now, one thing that's going to happen when we work with the 0, there is not going to be a sign change on either side of the 0 here, and that's because this root is repeated. So the 9 will change sign, but this one won't change sign. So now if we check by plugging in some values, like if I plug in a -1, let's say, I'm going to get -1 squared. It's going to be positive. -1 minus 9 is going to be negative. It's going to be negative over here. If I plug in a 1, I'm going to get 1 squared, which is positive, and 1 minus 9, which is -8, which is negative. It's going to stay negative. And then if I plug in some bigger number up here, like say 10 squared, positive, 10 minus 9, positive. Finally, I have a positive over here. So this is my sign chart, and I want to know where my polynomial is going to be bigger than 0. And so that's only going to be at 9 to infinity. Now, if this was equal to 0, oops, that wasn't what I wanted to do with it. If this was this, then I would have to include the point where it was also 0. So that would actually include, in this case, 0 and just the point 0 and 9 to infinity. So on this final interval, I would include the 9, sorry, a square bracket, but I'd also have to include this point over here, even though it's negative on either side. It's exactly equal to 0. And so that's a little bit tricky in this particular case. But our original problem was strictly greater than, and so I can ignore the fact that this is actually equal to 0 at that point. Now let's look at a rational example. Now, as with the polynomial cases, we want to work with 0. So we want to move everything over to one side of the equation. Now, the fact that the 0 is possibly equal to 0 is going to make things a little trickier for us, but that's fine. We need to find a common denominator in order to proceed from this point. So again, don't cross multiply up here and get rid of stuff in the denominator. You're going to lose your zeros. You're going to lose your sign changes. So we're going to put everything on one side, and now we're going to multiply x plus 1 over, or sorry, x plus 4 over x plus 4 to get our common denominator. And then on this side, we're going to multiply by x plus 1 over x plus 1 greater than or equal to 0. So our common denominator will be x plus 4 and x plus 1 in any order. And then our numerator will be 1 times x plus 4, which is just x plus 4, minus 2 times x plus 1. And then we can simplify x plus 4 minus 2x minus 2. Don't forget to distribute. X plus 4, x plus 1, and up here we have negative x plus 2. So x and minus 2x is negative x, 4 and minus 2 is positive 2, and it's this expression that is going to be greater than or equal to 0. So now where are our zeros? So the numerator is 0 at negative 2, positive 2, positive 2, and the denominator is 0 at negative 4 and negative 1. So let's draw our sign chart and figure out what our intervals are. So we've got 2, we've got negative 1, and we've got 4. And these two, again, I'm going to label them. These are from the denominator. So whether they get included in the interval or not is going to depend on whether they can actually be 0 or not. Things from the denominator are not allowed to actually be 0 because we can't divide by 0. So this is the only one that can possibly take a square bracket later on. Let's test some points. So these are all singular multiplicities, so the sign will automatically flip. So if I find one sign, then I can figure out what all of the rest of them are. If I plug in 0, this will be this interval. I'll get a positive up here, a positive down here, and a positive up there. That'll be a positive. Now, every 0 should, and every vertical asymptote should flip the signs. And I want to be greater than or equal to 0. So my interval at starts at negative infinity. There was a minus sign there. Negative infinity to negative 4. This is from the denominator. So whether the equality is included or not does not matter. I can't use 0 in the denominator. And then my interval picks up again at -1. -1 is also from the denominator, so I can't put a square bracket on it. But then I can go all the way up to 2, and that can take a square bracket because that's where the numerator is 0, and that will make the whole expression 0. Now, just as a side note, you can compare this to -x plus 2, x minus x plus 4, x plus 1 greater than or equal to 0. Now, the only difference for the solution to the inequality is at the zeros from the denominator. So if I were to find the solution to this, the solution here would be -infinity to -4 included, union -1 to 2 included. So all the signs, because I'm multiplying, dividing, that doesn't change what the signs do to the expression of the problem. Odd numbers are negative, odd numbers of negatives are negative, even numbers of negatives are positive, and you get exactly the same answer. The only difference is that you have to watch out for these brackets because the brackets are the things that are going to change. If this is all in the numerator, then I can be equal to 0, and so I include all of the zeros in this kind of an expression. But if I have a rational function, the ones that are in the denominator cannot be included, and so they get the round parentheses. But if it's easier to work with a polynomial, then you can do that and then just deal with the denominator factors later on. Particularly if you're trying to do this graphically, I find this particularly useful because sometimes rational functions, when you graph them, they kind of seem like they're all over the place, and polynomials are much more well behaved, but the sign changes are going to happen at the same places. But you just have to be careful when you have a greater than or equal to or a less than or equal to. Those equal tos are going to behave differently where the factors were originally in the denominator. If they're strictly less than or greater than, then the solutions to both problems will be literally identical.